Good afternoon, young people. It's Miss Stover here. I'm going to do another session, Bonding 3 session. This time we're going to be talking about more about ionic bonds, but we're going to be adding some polyatomic ions, adding some groups here instead of single element atoms. So topics that we're going to try to understand today are applying methods that we've already learned to ternary compounds, because the methodology is exactly the same. No matter what we do, the methods that we use are going to be exactly the same. So we need to keep that in mind and bear that in mind as we're doing our job. So the second thing we need to do is writing correct formulas for ternary ionic compounds and correctly naming ternary ionic compounds, even with D-block metals. All of this stuff is included. Remember, we talked about it being the layering. Well, we're adding another layer on to everything that we have. So let's look at the dot structure method. Well, let me tell you something. The dot structure method cannot be used here. The reason the dot structure method cannot be used here is because we do not know how to write dot structures yet for these polyatomic ions. So we don't know how to do that yet. So the dot structure will not work for us here. So we're going to have to skip that method and go on to the next method, which is the visual plus and minus method. So if we look at the visual plus minus method, let's look at an example. So we have Al and we have Cn 1 minus. Now, you might have been noticing that I'm not giving you a charge on the Al and wonder why that is. Well, it's because you know that aluminum is a representative element on the periodic table. You should know what charge aluminum is going to take based upon your knowledge of what should happen with aluminum's valence electrons. So if we look at that, we know that aluminum has 3 valence electrons and it will lose those 3 valence electrons rather than gaining 5. So we know that aluminum is going to take a 3+ charge. Remember, that means 3 electrons are being lost. And for the polyatomic ion here, the C and the N together, we know that 1 electron has to be gained. So the visual method says, okay, I have Al and Al has 3 pluses. That means 3 electrons that are going to be lost. And Cn has 1 minus. I'm sorry, let me finish the N. So for every electron lost, it has to be gained. So I need some more Cn. For every electron lost, there has to be a gain. I need more Cn. For every electron lost, there has to be a gain. Well, finally, I get it where all the electrons lost are gained. And so now what am I going to do? Well, I only have 1 aluminum, so I'm going to write Al. I don't write the number 1, I just write Al. Just like in math, if you have x, you don't write 1x, you just write x. So we're just going to write Al. But this is our issue. We have a group. We no longer have a single element. So we have to treat that a little differently. So when we have a group, we're going to take that group and we're going to put the whole group in parentheses. All the numbers, all the letters, everything goes in the parentheses. Then we're going to put the number of that group we needed on the outside. So that says I need 3 of the CNs. And yes, essentially that's 3 carbons and 3 nitrogens. No, I can't write C3N3. If we did that, we would have a list of polyatomic ions that would be 1,000 pages long and we'd never be able to use it. So we want to make sure that we can use it, so we keep the polyatomic ions simple at the lowest form, and then we put the number on the outside to show how many of the group that we had. So when we want to name this, we know what Al is. Al is a cation. It gets the name of the cation. So we call it aluminum. And then if I look on my polyatomic ion sheet, I see that Cn is called cyanide. So I just say aluminum cyanide. And that is the name of that compound. Okay, let's try another one, but this time we're going to use the least common multiple method. Okay, the least common multiple method, remember, says that we're looking at the numbers that are lost and gained. That means the magnitude. So we have Pb 4+, and I have to give you that because Pb can change charge, and O4 2 minus. So we look at the number, the 4 and the 2. We don't look at this 4. That means the number of oxygen with this group. This is the group right here. We can't change that group. Okay, so 4 and 2, the 2 magnitude of the charges. What's the least common multiple between those two? Well, the least common multiple is 4. So I need to lose 4 electrons and I need to gain 4 electrons. What do I need to do here? Well, I don't have to do anything because I should just need 1. So 1 times 4 is 4. But over here, to get negative 4, I have to multiply by 2. Well, you notice I got two numbers next to each other, so that's going to be a little issue there, but we'll take care of it. So we have lead here, so we're going to write PB. And notice I don't write a 1. I know there's 1 because I wrote PB. Now, because I have two numbers next to each other here, that means that I need 2 of this group. So the first thing I'm going to do is parentheses. I'm going to put the group in parentheses. Okay? Group goes in parentheses, and then I'm going to put the 2 on the outside. That tells me I have 2 of that group. 2 molybdenum and 8 oxygens make that up. Now what would we call this? Well, there are a couple names we could give this. One of the first names we could give it would be plumbic. Plumbic is the lead name for the lead 4, and then MOO4 is called molybdate. Molybdate. So plumbic molybdate would be what we would call this. Now the other name, and notice I'm writing the word or because you don't have to have both. The other name that you could name it is lead 4 molybdate. Lead 4 molybdate. Now remember, this 4 doesn't tell me the number of leads. It tells me the original number of electrons that needed to be lost. So that 4 tells me the electrons that need to be lost, the charge. All right, so that's the least common multiple method. The next method that we're going to be using is the switcheroo method. Okay, we know that the switcheroo method falls apart sometimes, and if we don't understand it, we shouldn't use it. So let's see if we can get an example here with a polyatomic ion. So we have Cr3+, and we have SiO3, 2-. Again, we have a group. It's a polyatomic ion. Polyatomic ions are just ions that have more than one atom together. Here we have 1 silicon and we have 3 oxygens. That's a group. We cannot take that group away. We cannot separate it. So we need to keep it together. Now the switcheroo method says, okay, the 3 becomes the number of this group I need, and the 2 becomes the number of chromium I need. So my formula should be Cr2. Remember, I need 3 of that group, so let me put the parentheses down first. SiO3, and then 3 on the outside. That says I need 3 of that whole group. Hang on.
Miss Martin, if you're still in the building, can you call the front office? Miss Martin, call the front office.
I love being at school. Okay, here we go. So what is the name of this? Well, we've got to look up this name. So we could call it chromium. Chromium what? Chromium 3 because of the positive number there. Chromium 3. And then the SiO3, we look on our purple sheet and we find out that SiO3 is silicate. So chromium 3 silicate. Or we could use another name because our purple sheet gives us another name for chromium 3. It calls it chromic silicate would be a perfect name as well. So both of those names work for these problems. So hopefully this will help you deal a little bit with these polyatomic ions. As you can see, the methodology never changes. The thing that changes is the way that we deal with the polyatomic ion and keep it together as a group, and then we throw how many we need on the outside. So don't be afraid of this. Just embrace it and try it and keep working with it.